Great, thank you. So I'm the first Matthias of the two authors here. Matthias Tealdi did this work of his internship. He's currently with Amazon. Unfortunately, he couldn't come. And I apologize for my voice. That's my poster session voice. So please bear with me. So basically, the problem we studied in this paper is right in the title. The game we are playing is that you have a textual documents which you don't want to share, but you're willing to share its n-grams and the counts of these n-grams. And now my purpose is to reconstruct the document out of this count I have, or you're giving me. So why we're doing this? Xerox, the company I work for, is a B2B company. We do business to business. This basically means that the business lines who contact us, they many times do not own the data. They're asking us to do some data analytics on top of it, but they're actually documents which belong to the clients of the business lines. And this means that sometimes they can't even share this data with us because there were some legal constraints or some privacy constraints. And then someone there was the idea, okay, if you just give us the n-gram count, maybe we can run all our algorithm on it, and we will never know what's the original data behind it. Another motivation was that's a paper from ACL, which talks about a machine translation marketplace setting where machine translation players would share their phrase tables. That's kind of a very important data resource. And so everybody would share these phrase tables, but again, the companies, they may not be willing to share the original documents, so you want to avoid that people could reconstruct the original documents. And then the final one may be copyright concerns. This is a snapshot from the Google Ngrams. I guess many of you know it already. So basically, the people, they scanned millions and millions of books. They can't release these books to the public because it's copyrighted information, but they can release Ngrams count, right? So in all these cases, the things we're studying here are basically the two sides of the problem. One is you give me Ngram information, I want to reconstruct your document. And then I take the other side and say, okay, if I would have a document I want to share because I have to or I want to or for whatever reason, what would be the best way of dealing with this data so I can still share it, but you can't reconstruct the document which is behind. So let's go with an example. That's a running example we're going to have. That's a document which consists of the sequence. Just for clarity, I added a begin and an end of marker, begin end of marker document. And document marker. And so this is not really needed for the algorithm. It's just to make things a bit easier. So I'm assuming that I don't see this document. What I see is this kind of table, in this case for bigrams. So these are all the bigrams of the document together with their count. And maybe a first thing to notice here is that this is a lossy representation of the original document. So in this case, there are two other sequences which generate exactly the same table. So this is the first impossibility result, basically, which is telling me that in the general case, I won't be able to reconstruct exactly the document that you have hidden, because there may be more than one which could lead it to exactly the same table. So we reformulate the problem a bit, and what we will be looking afterwards is to find larger chunks of text on whose present in the original document we are totally sure that they have to occur. So basically, we want to take this table here to enlarge it somehow, and to find bigger chunks of text. And so the way we are doing is we are encoding this in a graph. That's a subgraph or something called the Bruijn graph. It's used in bioinformatics and in graph theory. So the edges here are the n-grams you just saw, in this case bigrams. The nodes corresponds to n minus 1 grams. And then there is an edge here, basically, if there is an occurrence of this n-gram here. And now you have this graph, and if you start walking through this graph, it's a directed graph, then you would have possible chunks of text which may or may not occur in the original document, right? So if you would take the path 2, 2, 3, 1, what you would have is rows is okay, and then if you continue walking through these things, you start creating bigger things. Now these things may or may not occur in the document, right? It's just one way of constructing them. Now, what you can figure out is that if you would have a path which touches each edge exactly once, then what you would have in the end is a plausible reconstruction of the table that gave place to this graph here. Okay, that's basically what I'm saying here. If you have an Eulerian path on top of this graph, this is a plausible reconstruction of of the document. And then, as I said before, the challenge is to find those parts which are common in all Eulerian passes, because these are the parts I know with 100% certainty that they have to have occurred in the original text. The big problem here is that there are many, many Eulerian passes. It's a famous theorem from the 50s. Basically, just explodes the number of possibilities. So you can't just generate them all and walk through them. So what we're going to look after is basically finding, you can see it as an intersection of all possible Eulerian passes, and try to find what are these intersections. Now, the way we're going to do this is that we have some passes here, some subpaths of possible Eulerian passes, which we know have to occur in all cases. So this is an example. You know that if this path here, 0, 1, 2, has to occur in all possible Eulerian passes in this graph, right? Because there's no other way of leaving zeros and going here. There's no other way of leaving ones and going here. So basically, this is a trigram which you can deduce based on the bigrams that you have. And that's the game we're going to play, right? We're going to construct bigger and bigger grams and until we can't anymore. So that's the only slide with a bit more formal definitions I have here. It's just to make sure that the goal is clear for everybody. What we have is this EC of G. And sorry, I'm pointing to the central screen, just if you want to follow. The EC of G is a set of all Eulerian passes. I'm assuming I have this label, the labeled of a possible path. And then S of C is the concatenation of all these labels. So it's basically the possible reconstruction of this given Eulerian path. And what we're after, we are starting with a graph G, which you saw before. We're looking for a graph G star, which has two conditions. One is it has to be equivalent, meaning that all Eulerian passes in G star has to be, the set of Eulerian passes in G star has to be the same than the one in G. We don't want to invent new stuff or to take stuff out. And then secondly, it has to be irreducible. And irreducible here means that there are no two adjacent edges which occur in all Eulerian passes of G stars. Because if they would be, we could just concatenate them and we would have a graph which is even more reduced. And then once we have this G star, we can just look at the labels that we now have on these edges. We read the labels from there, and we have our maximal blocks that we're looking after. So to give you an idea, that's an irreducible graph which corresponds to the graph we saw before. It's pretty easy to see here that you have, easier to see than before, that you have 3 possible Eulerian passes from 0 to 4, which corresponds to the 3 possible reconstructions of my table. And so this is the final output of the algorithm. And what we then do, we just look at the labels of the edges, and these are our maximal blocks. So here we have rows as a rows, which is a foreground, and which is basically something on which we are sure had to occur in the original document. Okay, so as I said, that's what we are playing this game here, and what I'm going to show you is going to be 2 different rules, which you can apply on these graphs. And the main theoretical result of the paper is that we have a proof which tells you if you apply these rules until you can't anymore, then the final graph that you obtain is equivalent and is irreducible. So I'm going to explain you shortly these 2 rules, just with intuition. The formal definitions are on the paper if you're interested. That's the first rule here, an example of the first rule, better to be more correct. So what we are seeing here is all the neighborhood of a node X. And node X has 3 incoming edges and 3 outgoing edges. Now notice that you have one incoming edge here, alpha, which occurs very frequently. So all Eulerian passes has to enter X through alpha exactly 8 times. And now assume take into account the 4 first time that the Eulerian passes enter X through alpha, and assume what I will call the worst case, that these 4 first times, it leaves either through epsilon, so twice, or through zeta twice. Even in that case, there are still 4 more times when my Eulerian pass has to enter X through alpha, where the only way where I can leave, because everything else is kind of full, the only way that I have to leave X is now through delta. Okay? So the idea here behind what I call it the Pigeonhole Rule is that we know with total certainty that alpha concatenated with delta has to occur at least 4 times in my original document. And then what I do is I create this new edge, which now has a label which is a bit longer than the original n-grams, and I deduce the multiplicity of the other two edges. Okay, so that's the first rule. This is a 100% local rule. I only look at one node in its neighborhood. And there is another rule, sorry, which takes into account more the global structure. Now, in this example here, all edges occur exactly once, except alpha, which occurs twice. I can't apply the pigeonhole rule here on top of x. But this graph has some important property, and it is that x is the articulation point, it's called in graph theory, of this graph, which basically means if you take x out, it divides your graph into disconnected components. Okay, so you will have two components which are connected by something, but they're not connected between them. And now the intuition I want you to get here is that the only way of getting from the left component to the right component is through alpha, through x, and even more, it's the only way of entering x from the left component is through alpha. The only way of leaving x to the right component is through beta. And this basically means that we know that alpha beta has to occur at least once in my original data. And I do the same thing as before. I reduce the multiplicity. So I'm going back just so you see the difference. Beta occurred only once, so I reduce the multiplicity. It disappears. And the edge alpha loses one occurrence. Okay, so these are the two rules I have in my toolbox. And what I now have is this theorem, which basically tells me that if you apply these things until no precondition of these rules hold anymore, then what you end up with is a G star. It's a graph which is equivalent and it's irreducible. Okay, so that's a theoretical result. We looked at how this performs in practice, and for this we took books from the Gutenberg project. These are out of copyright books which are freely available. And what we did, we took a couple of these plots are on single books only. So it's maybe hard to see, but what we have on the x-axis in both cases are the n-grams. So we consider from bigrams to 10 grams. And the left plot shows you the mean average size of these maximal blocks that we obtain. So just to give you a number, if you consider 5 grams, which is kind of a popular n, the average size that I obtain out of the book are about, I think it was 54, something like this, 54 words. Okay, this corresponds to 3 or 4 lines of a standard book. To the right, we have a similar plot, but now we have the maximal size. So it's the biggest guy I could obtain. And here again, for 5 grams, what we obtain is 350 or something like this. And this is a standard paragraph, let's say. Okay. So you have your book, you give me 5 grams, and what I obtain a chunk of, at least one chunk of text in general, which has the size of a paragraph. This is considering only single books, okay? Now you can ask if you have more than one book, if you have a concatenation of several ones, this is a more realistic case. What happens is that you have more diversity, and in the algorithms, it basically means that you're less sure on which of these blocks occur in the text. So the average size of your blocks actually decreases because you have many few ones. But this plot here shows you the average number of large blocks, where I just decided the large blocks are blocks which have more than 100 words. And what you can see is that the number of these large blocks, this is for 5 grams again, it keeps increasing. So you give me more and more data, and I can find larger and larger blocks on which I now have to occur in data. A standard way which people could think that to avoid this problem is that you would say, okay, I just remove stuff. I don't give you the complete data, perfect information. This was the assumption until now. But I add some kind of noise, and then a standard way of adding noise to say, okay, I remove the low-frequent n-grams. Because anyway, they're probably not important for your statistical algorithm, so just throw them away. So what we did is we did the same thing. We run our algorithm again on top of them. And now the x-axis here is m. So it's a threshold which your n-gram count has to have in order to be kept inside the corpus. The blue crosses, the axis on the left, shows you the mean block size. So basically, it has, at the beginning, it has a weird phenomenon. There is an explanation for this. But then it keeps increasing. So your mean size keeps increasing. That's basically because you have fewer and fewer blocks. and because you have fewer and fewer data. And so you have few blocks, but they're actually bigger and bigger. Well, no, they're not bigger and bigger, but you keep the big guys. And that's what you can see in the red plot, whose axis on the right. It's basically telling you that the biggest guy you keep keeping it. So red is again the mean maximal block size. Now, not all of these blocks are correct now, okay, because the theorem only holds for perfect information. So we plotted error rate, and this is the blue line here is the general error rate for all blocks together. And you can see you reach a maximal of 5% of error rate, and then it keeps decreasing, basically because what you find is fewer things, but you're more certain that they're actually correct. And I have the same plots for blocks which are bigger and bigger, and basically it's telling you that the big guys that you find, they're mostly correct. Okay, you have a 0.5% of blocks larger than 25 which are incorrect. Okay, so most of the blocks are correct. So we thought, is there a way of doing a bit better than just removing stuff? And we came up with the idea that instead of removing n-grams, to add n-grams. So these are n-grams which didn't exist before. You basically invent them. They're stuff which didn't exist in the corpus. And the important thing is you just don't add any n-gram. You have to choose them somewhat strategically. Now, these are chosen in such a way that they break our own algorithm. Okay, so it's a bit of cheating here. But okay, that's what we did. And what I have now is, again, the error rate with respect to the number of modified edge. That's to be able to compare both methods. The blue crosses here in this corner correspond to the error rate we saw before. So you remember that they were always less than 5%. And you're modifying lots of edges, right? And now these red dots here corresponds to adding this amount of edges. And you can see that the error rate just, well, it increases much, much larger. And with much fewer modified edges, you obtain an error rate which is much larger, or more than 20% of error rate. Now, adding noise, just for the sake of adding noise, is something easy. You could just mess up your data and give it away. We still want the data to be useful. And then in order to ground the notion of usefulness, we consider perplexity of the language model. And so what we are plotting here is exactly this, is perplexity of the language model. And if you remove stuff, what we are showing here is that the perplexity actually just grows a lot. This is actually logarithmic of perplexity, so it's much worse. While if you add things, the growth is much more smoothly. And in any way, the scale here is very different. Okay, so it's everything I have to say, and I have to stop. So I'm happy to take questions if there is time.
Okay, thank you.